In this section, we will build up data structures to describe the state of a biological system. At any given time, you can think of a cell as having a complex data structure ultimately composed of atoms. There are changes in state of these atoms in terms of their position, constantly occurring. That is the mechanistic underpinning of the dynamic behavior observed in biological systems. One way to model a cell is to describe it as a set of particles. Those particles have a position, a velocity, and based on this species description, they have some identity that defines their behavior. At the most basic level, we can discuss four classes of species: photons, atoms, molecules, and complexes. The photon is entirely defined by its wavelength, which is a real number expressed in nanometers. An atom is defined by its number of protons, neutrons, and electrons. Based on the number of protons, one can look up the name of the atom, like carbon or sulfur, so we don't have to include both pieces of information. Num protons is sufficiently expressive. All these counts are integers because each particle is itself quantized. You can't have half an electron. A molecule is a structure representing a graph of atom objects connected by covalent bonds. Finally, a complex is a structure represented by a graph of molecules held together through non-covalent bonds. There are many ways of expressing this graph that is a molecule. Here we see 8 different but equivalent ways of expressing the structure of the molecule in aspirin pills. For visual consumption, you can draw an all-atom structure showing every bond in every atom in the molecule. These are cumbersome to look at and draw, so this representation is rarely used. Organic chemists will typically employ a condensed version of the all-atoms view by omitting all the hydrogens bonded to the carbons. A ball-and-stick model captures a three-dimensional conformation of the atoms. It captures the structure, the length of the bonds, and their relative positioning. A space-filling model is like ball-and-stick, but it also captures the radius of each atom and thereby gives the viewer one notion of the surface shape of the molecule. For verbal communication, there is a formal rule-based nomenclature called IUPAC, but older names that are common names persist. Because IUPAC names can get long and cumbersome, many people prefer to use the common names. For computer-readable serialization, the SMILES and INCHI formats capture the structure of the molecule as a short string. All these representations ultimately. A graph is mathematically defined as an ordered pair of two sets. One of these two sets, V, is the set of nodes. For a molecule, each atom is a node. The other set is the set of edges, which is itself expressed as a set of ordered pairs of nodes. To encode a graph in Java, you would declare a class called graph that is composed of a set of nodes and a set of edges. Nodes would be a class that perhaps have a label such as name, and the edge is a pair of two nodes. In this case, the edge has directionality. We distinguish the from and the to nodes. To express a graph representation of a molecule, we would encode the molecule as a list of atoms and a set of bonds. A list in Java means an ordered list. Each atom will have a specific index or position within this list. We have already defined the class atom as being 3 integers for expressing its number of protons, neutrons, and electrons. We then can express the bonds as being integer pairs referencing the position of the atom in question from the nodes list. For purposes of discussion, I'll simplify our representation of the molecule to just a list of character, in which we use the letter codes like C for carbon, O for oxygen, and so forth to describe the atoms. Let's look at an example of the graph representing ethanol. I'll arbitrarily assign an index to each atom in the molecule. There are 9 atoms, so there are 9 indices, and my list of atoms will have a size of 9. If I now list out the letter code for each atom, I construct the atom list. For each bond in the molecule, I'll express the indices that the bonds connect together. So for example, the leftmost bond between hydrogen labeled 0 and carbon labeled 3 would be a bond 0, 3. Stereochemistry deals with the fact that two molecules can be identical in terms of the attachment of the atoms, but nevertheless different in three-dimensional shape. For biological molecules, this comes from the fact that carbon has 4 bonds, and when in an sp3 hybridization state, having 4 different things attached to the carbon atom can be in 2 different configurations that are mirror images of each other. Because of this, many organic molecules are chiral, and their mirror image is a distinct molecule. Note that this representation I provided for a molecule neglects stereochemistry. This could be easily remedied by introducing a list of booleans to represent each atom in the node list as being either the R or S configuration. Though stereochemistry is important to accurately describe things, we will ignore it for the sake of simplicity for now.